Yes, sir.
Is being recorded. Okay. So we repeat. A raised to n, B raised to n, C raised to n. This is not a context-free language. We can't have a PDA except in this language. Neither non-deterministic nor deterministic. Once again to repeat, among models of computation, mainly FA, PDA, and Turing machines. FA and Turing machines, whether deterministic or non-deterministic, they are equal in power. When we say equally powerful means same class of language accepted by them. Whereas PDAs, non-deterministic PDAs are more powerful than deterministic PDAs. There are certain languages which can only be accepted by non-deterministic PDA. For example, the language of palindrome. So this A raised to n, B raised to n, C raised to n, this is not a context-free language. With FA plus stack, we cannot accept such a language. Two examples we had given in the beginning of languages that are not context-free language. One is this one, and other was SS, where S belongs to AB star. First part symbols, same as the second part symbols. A double B, A double B, for example. So here, only Turing machine is possible. We don't have finite automata. We cannot have PDE except in this language. This is not a CFM.
Sir, this can be accepted by a non-deterministic PDA or no?
No, 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 no.
Okay.
And
Yeah,
also,
yes,
sir, if
yeah.
possible today, as today is the last lecture, can you focus more on revision also?
Yeah, maybe no. About maybe 5 minutes we can discuss that. Then no, you have to complete the syllabus. A lot of things are remaining.
Okay, sir, because
But then maybe yeah, we can have say 5-10 minutes discussion right now. 5 minutes discussion right now. Then I will continue with this, and maybe at the later. Deepali, maybe this is not a technical talk. You may just stop this the recording for time being. And after this topic is over, we can
This
discuss.
meeting
Is being recorded.
sir, started.
Yeah. So A raised to n, B raised to n, C raised to n. This is not a CFL. We can't have FA or PDA. We construct a Turing machine. Blank R. My input format is blank X. The content of 0th cell is blank, and from cell number 1, my input begins. So blank R. I am taking head to the first cell, and those Q1, Q2, Q3, Q4 you can see 1A, 1B, 1C we are counting. So from the first part, leftmost A, from the second part, leftmost B, third part, leftmost C. From the unmatched A's, B's, and C's. So look at Q1 to Q2, small a, capital A, R. So capital I is my marker. So when I return back, if it is capital, I know I had previously made that. Once I convert small a into capital A, so 1A matching is over. Now I have to find 1B and 1C. So in the state Q2, remaining is that is small AR and B's that are already matched in the second part. Those are capital B R. And in the state Q2, finally, when I get small b, I convert it to capital B. So one small a, one small b. They have matched. I continue moving towards right. State is Q3. Then remaining b's we do not consider right now for iteration. One small a, one small b, one small c. And once they match, they become capital A, capital B, capital C. And we do it for every symbols. So Q3 state, BPR, unmatched B, part number 2. Then I go to part 3, again matched C, that is capital CR. And in the Q3, when I get small c, I convert into capital C and L because one A, one small b, one small c converted into capital A, capital B, capital C. They have matched. Now I am returning. From Q3 to Q4 CCL, I have started returning. Unlike other models of computation, so the input can be scanned any number of times by Turing machine. So Q4 state, CCL, so unmatched, I mean already matched C's, those are capital C, capital CL. Then BBL, small BBL, again, and small a. So the things which are yet to be matched, those are small a, small b. Already matched B's, capital Bn, and when I get capital A, I'll start next iteration wherein I'll match one small a, one small b, one small c at the respective position. So when I get capital A in the state Q4, it is capital A R. So I go to state Q1 and start again a new iteration. So that is how I count A, B, and C. 1A, 1B, 1C. I match. Eventually in the state Q1, because of AR, when my matching is successful, assuming that my string is of the form A and B and C, and because of AR, I'll get to the first capital B finally, when everything has matched. State will be Q1. Therefore, it is BBR, capital BR downwards, Q1 to Q5. Then I continue moving towards right. So BBR is BBR, then again CCR, and then blank blank S. After my input, we have infinite number of blanks towards right. So in the state Q6, it is blank blank S and halting state. And we are ensuring that because we are matching from left 1A, from left 1B, from left 1C, and in that order, left to right. So in the right, we should only have capital B's and capital C's. We should not have any other symbol. Therefore, we have Q1 to Q5 BBR, then BBR, Q5 to Q6 CCR, then CCR, to ensure that no other symbol is there when we reach to the halting state. Once we reach halting state, no need to further process input. That is how a TM operates. The other models, we process the total input, whereas here, once we reach the halting state, then the string is accepted or the processing is complete. And of course, part 2. The one thing that is remaining is this Q1 to, suppose n is greater than or equal to 0. If n is equal to 0, I won't have small a. So from Q1, I will directly jump to HA. It is blank blank yes. When the input is blank, my n is capital is n is greater than or equal to 0. So when n equal to 0, I don't have something like small a, small b, small c. Maybe we can think about merging this Q5, Q6 because it is BPR, CCR, CCR. So can we reduce one state like having BBR, CCR like this? So we should just check out that a string such as ABC, ABC should not be accepted. Strings such as ABC, ABC, though it has two A's, two B's, and two C's, but it is not of the form AA, BB, CC. So while merging this, we should be careful that we don't have this combination. However, that this all A's, then all B's, and then all C's, that sequence is taken care in the first part itself here. Is taken care in this part itself. So we can merge these states Q5, Q6. We can reduce to one state, and still that should be fine. You check out yourself also for satisfaction. So this was A raised to n, B raised to n, C raised to n. Language which is not a CFL. So no question of being accepted by finite automata or push down automata. Only Turing machine exists. And we constructed a TM for accepting that language. Now defining a Turing machine, a TM for computing a function. TM, those are 5 tuples, Q sigma tau, Q0 delta. We don't have the accepting state because our accepting state is HA, which is compulsory. HR is our rejection state, which is optional. So we don't have a set of accepting states. Rather, we have this tape alphabet, which is tau. Other symbols are as usual. And meaning of computing a function, TM computes a function. So every x that belongs to sigma star at which f is defined. So we are talking about a partial function, which is defined at some points in sigma star. So for every point that on which the function is defined, every point, every x on which the function is defined, my input is, this is my input configuration, Q0 blank x. T, when holds, after computing it, the output will be blank fx. So my input is x, output is fx for every x on which the function f is defined. So my initial configuration, when we say initial configuration, is the initial state which is Q0, blank x, x is my input, Below blank that's the initial position of the read write head, therefore that underscore is present. That's the initial position of the read write head, that is over cell number 0. Output is fx when function holds. Output is fx when the TM holds. At that time function is computed. That is the meaning of computing a partial function. For every x in sigma star on which the function is defined, this is my initial configuration q0 blank x. My output configuration is ha blank fx. And for every other x belongs to sigma star on which the function is not defined, all those x's are not accepted by T. It doesn't hold. For every x belongs to sigma star at which f is defined, it holds, and at that time the configuration is ha blank fx. And for any other x belongs to sigma star, it doesn't hold. Now instead of one parameter, if we have multiple inputs, we have taken one input x. Suppose we have k number of inputs, x1, x2, xk, then this will be my configuration. We take this is a k tuple on which the function is defined. My k tuple is x1, x2, xk. So my input is q0, then blank x1, x2. So each of these parameters x1, x2, xk, they are separated by blank. So blank x1, blank x2, blank xk. So this is my initial configuration q0, and then my input. We have such k number of inputs, and for this k tuple of inputs, the function is defined. So it will hold, that is ha, and it will compute f of x1, x2, xk. It will hold and compute f of x1, x2, xk for any k tuple of input on which the function is defined, and for every other k tuples, it won't hold. It won't accept, it won't hold. And no other input that is k tuple of strings is accepted by T. Function is said to be computable if there is a Turing machine computing the function. Partial function f is said to be computable if there is a Turing machine computing the function f. What is the meaning of computing f? This is the meaning. There are k tuples here. If there is a single parameter, this one. That's fine. We'll take examples also. Now this was all about functions on strings. Now we talk about numerical functions. So the difference is unary representation. Here it is unary representation. If my input is n, then on the tape I'll put n number of ones. So if my input is 5, then my initial tape content would be blank, then 1, 1, 1, 1, 1. We have 5 number of ones. That is the meaning of unary representation. Computing a numerical function, same. My input is n, and how to represent n? By n number of ones. So it is 1 raised to n. There are n number of ones. So a point integer value on which the function is defined, for that the initial configuration will be n, output will be f of n, and this is unary representation. So n is n number of ones, that is 1 raised to n, and my f of n, whatever is that integer, that many number of ones. So T computes f. If for every n at which f is defined, my input is n, output is f of n at the time of halting, and that is represented, fn is represented using 1 raised to fn, n is represented using n number of ones. So for example, this is a square function. My input will be 5, output will be 25. So initially on the tape I will have blank, then 5 number of ones, and at the time of halting we'll have blank, then 25 number of ones. So that is 1 raised to fn. This is on every n at which the function is defined, and it will not hold on any other natural number. Similarly, you can have multiple inputs. K tuple. There are natural numbers n1, n2, nk. This is n1, n2, nk. Initial state is q0. Unary representation. Output will be f of n1, n2, nk. Again unary representation. So 1 raised to that much. For every k tuple of n on which the function is defined. So it is a mapping from, it's a partial function mapping from n raised to k. There are k n's. There are k natural numbers, n raised to k, and output is one value. So it is n raised to k to n. It is n raised to k to n. There are n1, n2, nk, and output is a single natural number. It is n raised to k to n. Basically, a TM accepts the language domain of the function. TM accepts the language domain of the function. The points which are not there in the domain, for those points, the TM will not hold. It accepts the language domain of the function. The partial function means defined at some points. Total functions means defined at every point. So this is theory about computing a function. We look into more examples, application of this theory. Examples, computing a function, and the function that we compute is n mod 2. The function we compute is n mod 2. TM is a general, Turing machine is a general model of computation. Not only it can recognize languages, but can also compute functions. So here we have defined computing a function, meaning function on strings, and function on integers, function on numbers. Right. So we compute n mod 2. Turing machine to compute n mod 2. Again, my input n is binary representation. Look at this: Q0, Q1, Q2, Q3, Q4, HA. So if my input is an odd number, then required output is blank 1. This is a remainder function, n mod 2. So the remainder will be either 0 or 1. So if my input is an odd number, then my output is blank 1. For even natural number, the output is blank. Turing machine to compute n mod 2. Remainder is either 0 or 1. So this is simple. My input is binary representation. Say initially the text content would be, for example, blank, then n. And because it is binary representation, it's n number of ones. For example, blank, then 5 ones. 1, 1, 1, 1, 1. My input is 5. Output will be blank 1. 5 mod 2. Remainder is 1. So output will be blank 1. And the position of the read-write head, that is over cell number 0. And if it is even, the input is 4. That is blank 1, 1, 1, 1. And the output will be empty. Is 0 remainder. So required output is this. This is my problem statement. So what do we do? Go to the rightmost one. This is my typical move Q0 to Q1 blank blank R. And in the state Q1, it is 1, 1 R. So I am going to the rightmost one. In fact, blank after the rightmost one. 1, 1 R. I'll go to the first blank after the rightmost one of the input. After the rightmost one of the input. So that blank, I'm doing blank blank L. In the state Q1, I'm moving from left to right. So my input will get over. My input is all ones. It is exclusively ones, only ones. So after my ones are over, I have, because state is infinite in length, I have remaining squares as blanks, infinite number of blanks. So when I get first blank from the left, I'll go to the last one. So that is blank to blank 1. My current state will be Q2. What we do now, by moving towards left, we erase 2 ones at a time and in a single scale from right to left while moving towards left. So we'll erase 2 ones. And why do we do that? Because eventually I require the content of cell number 0 as blank and the content of cell number 1 as 1 if the number is odd, or content of cell number 0 as blank. So what we do while moving towards left, that is a loop between Q2 to Q3, we erase 2 ones. We erase 2 number of ones. 1 blank L, Q3, Q2 to Q3, Q3 to Q2, again 1 blank L. So we erase 2 number of ones and continue moving towards left. So we remove 2 ones. Eventually, there will be a single one if my number is odd, or there won't be any one if my number is even. So that is 1 blank L, 1 blank L. And if, assuming that my number is even, so from the Q2 state, finally, I'll reach cell number 0. And as per our notation, the content of cell number 0 will be blank. So in the state Q2, I get a blank. I'll stop. I'll go to the halting state. already the required output blank. Required output blank is achieved. This was the even number. In case it is odd, so in that case, in the state Q3, I'll get a blank. This Q2 to Q3, that was the remaining one. That was the remaining additional one. And subtracting two ones. So finally, there will be a single one left in the case of the number being odd. That one I have already erased, one blank L. I don't have any more one. So what I do, because of one blank L, I am going to cell number 0. There, cell number 0, I am performing blank blank R. So I go to cell number 1, write 1 there, write 1 in cell number 1. So that is blank 1. And again L, because we have to go to cell number 0. The position of the read write head at the time of halting should be cell number 0. Required output is blank 1. Required output is blank 1 when the number is odd. So that is the move path Q2 to Q3 to Q4 to HA. That is my odd number. Even number finally Q2 to HA. Only required output is blank and the position of the read write head should be over cell number 0. So we don't do anything. It is blank blank S. Already we are there on cell number 0. We cannot write L. If you say L, we'll be going to the left of the 0th cell, which is a crash, which is a rejection of the string. So we have to be very careful. Q2 to HA, it must be, the displacement must be S. The movement of the read write head should be stationary, no movement. So that is blank blank S. So this is N mode 2. It will compute like this. Turing machine to compute N mode 2. Similarly, if it is N mode 3, your triangle Q2 to Q3, Q4. Same logic. We'll move from left to right, go to the first blank after my input, and then return back. And while moving towards left, we'll erase three number of ones. My remainder will be either blank divisible by 3 or 1 or 2. So there, this remainder 0, then this is the output. Remainder 1, then blank 1, remainder 2, blank 1, 1. So that's the loop Q2, Q3, Q4, back to Q2. So if the remainder is 0, from Q2, I will directly go to the halting state. 1 blank L, 1 blank L, 1 blank L. Moving towards left, we are erasing 3 number of ones. Suppose my input is 6. So 3 ones, one more loop, 3 ones erased. And because of L displacement, finally we'll reach cell number 0. So from Q2 to HA, blank blank S. The remainder is 0. We are already over cell number 0 and we have to keep read write head over cell number 0. So the displacement is stationary, no displacement. That is blank blank S. Similarly, Q2, Q3, Q8, HA, in that case, remainder is 1. So single one was remaining that we have erased between Q2 to Q3. We'll write single one and then halt. Remainder is 1. Remainder is 2. Then the path is Q2, Q4, Q5, Q6, Q7, the bottom one. Already we have erased 2 number of ones. So between Q2, Q4, Q5, Q6, Q7, look into that. See, Q2 to Q3, my remainder is 2. So there are 2 additional ones. So Q2 to Q3, I have erased 1 additional one. Q3 to Q4, I have also erased the second one. And because of L displacement, I am at cell number 0. State is Q4. So blank blank R, that is Q4 to Q5. I go to cell number 1. State is Q5. On cell number 1, I'll write 1. So that is Q5 to Q6, blank 1 R. Q6 state, one more one is to be written because remainder is 2. So Q6 to Q7, blank 1. So say this is second one which I am writing. Now I am start returning because the position of the read write head should be on cell number 0. Remainder is 2. The position of the read write head should be on cell number 0. So that is blank 1L, Q7 state. Then it is 11L. So we go to cell number 0 and we'll stop. We have written 2 ones. The thing which is not visible between Q7 to HA is 11L. So we'll go to, because of L, we'll reach cell number 0. We are writing 2 ones which we have wrongly erased between Q2, Q3 and Q4. Remainder is 2. We are writing between Q5, Q6, Q7. And because of 11L, subsequently reaching cell number 0. So that is N mode 3. Computing N mode 2, extension, very simple extension is N mode 3. So here was a loop between Q2, Q3, and here there is a loop between Q2, Q3, Q4. That is N mode 3. Next example of computing a function, that is a copying a string. That is copying a string. Third example, computing a function. N mode 2 we have seen. N mode 3 we are looking at. We are looking at N mode 3. Sorry, we have looked at N mode 3 in the last example. Now we are looking at copying string. So input is blank x, output is blank x, blank x. This is my problem statement. X belongs to sigma star. Now this is no more unary representation. Not working on these numbers. Not working on these natural numbers and unary representation. Next example, the ninth example actually, third example of computing a function. It is for copying a string. My input is blank x, and when we hold, the output should be blank x, blank x. So content of cell number 0 is blank, then my source string x, then I'll keep a blank, and then my copied string x. And not only that, I must reach back to cell number 0. So that is underscore, that is below that blank x, underscore specifies that at the time of stopping, the position of the rewrite head should be over that particular symbol, which is nothing but cell number 0. The content is blank. So this is my problem statement. Q0 to Q1, blank blank R, because my input begins from cell number 1. Content of cell number 0 is blank. My input format is blank X. Initial position of the rewrite head, that is over blank, which is cell number 0. Blank blank R, I'm going to cell number 1. Now X begins. The source string begins. X belongs to sigma star. So state is Q1. Assumption sigma is A comma B. My input is made up of symbols A or B. And as a marker, the symbol which I read, I convert into capital letter. And then after the first blank, after the source string, I copy the first symbol, then the second symbol, third symbol, etc. So Q1 state, my leftmost symbol could be small a or small b. If it is small a, I take the upper branch, convert into capital A as a marker so that I don't copy it again. So small a, capital A, R. Then in the state Q2, it is small a, R, small b, R, because the remaining symbols of the source string I don't copy. For iteration, I copy one symbol. So in the state Q2, I skip 100 symbols in the source string. Then I get a blank. After my input string X, I have to keep one blank and then copy X. So that is blank blank R. I go to state Q3. Whatever symbols I have copied so far, I skip. That is small a R, small b R. Second iteration onwards, I'll find some symbols. These are the symbols that are already copied from the source string. The first iteration, what will find? I'll find blank. In the state Q3, in the first iteration, I'll find a blank. I'll write A there and again return to the next symbol to be copied. So L is the displacement. Again, I'll return to the next symbol. And in the state Q6, I'll skip AL, BBL and blank blank L. AL and BBL, AL, BBL are the destination string, the partial string that is copied, that is skipped through AL, BBL. Then there is a blank, so there is blank blank L. And then in the source string, there are uncopied, unprocessed or uncopied symbols. Those are also skipped. When I get a capital letter, I know that symbol I had copied in the previous iteration or in the current iteration. I have already copied that. So a symbol to its right will be copied next. So when I get capital A or capital B, I revert that into small b, because my required output is blank x, so x is in small in letter. So I can't keep that as capital. So when I get capital A, capital B, I again restore back to small case letters, and R is the displacement. So I'm ready for copying the next symbol back in the state Q1. So whatever I have done in state Q1 for symbol A, small a, when it is symbol B, just complement of, very analogous to what I've done there. Here in the state Q5, on getting blank, I'll copy B. Left hand side B was there, right hand side I'll copy B. In the upper branch, left hand side A is there in the left. From the state Q3, I'll copy small a there. So once I have copied everything, I'll be in the state Q1, and because of this Q6 to Q1 move, the displacement in that move, the displacement is R. So when my entire string is copied, because of R displacement, I'll get a blank. That is a separator blank between my source string and the destination string. By the source string and the copied string. This is the one blank I have kept. So eventually, when the copying is over, I'll be in the state Q1 and I'll find a blank. When I get a blank, I don't need to do much except to take retrieved head over cell number 0, because that is my required output, blank X, and the position of the head over cell number 0 over that particular blank. So in the state Q7, I'll just skip the symbols of the source string. L is the displacement. Eventually, I'll reach cell number 0, and I'll halt there. It is blank else. Halting state has to be there to accept a language. There has to be a halting state. HR, the rejection state, may or may not be there. It's not compulsory. Delta QA equal to 5, it means delta QA equal to 5 means for a state symbol, I don't have a move. Then it is crashing. It is same as reaching to the reject stage. So this is for copying the string. Input is blank X, output is blank X. The third example of computing a function we have seen here. Is that fine up to this point? These examples? Some feedback, students? Anyone?
Yes, sir.
Okay. Everything, any doubt to anyone?
No, sir.
Okay. Next example we see for copying a function. This is reversing a string. Reversing a string. Previous little difficult example was SS. Because in that case, the SS case, we didn't know where the second half began. We didn't know where the second half begins. Because my input can be of any length. For any input, we should be able to detect whether the string is of the type SS or not. We didn't know where the second half begins. So we have to identify, we have to split that into the first part and the second part and remain somewhere, either at the beginning of the second half or the end of the first half, so that we can separate out first half and the second half. Whereas here, this A raised to N, B raised to N, C, and all these examples, we know where exactly the 1/3 begins, next 1/3 begins, because those are A's, B's, and C's. We don't need to identify that. Now, next example is for the reversing the input string. Reversing the input stage. Here we have to take care. This is also a little complicated example where we have to take care for 4 possibilities. What we do? We reverse the first. We extend the first symbol with the last symbol. We exchange. We take one symbol in the left, and then we copy the symbol to the right at the appropriate position. Also remember the symbol that was erased. Bring that back to this particular position. We swap that. So this is for implementing the reverse function. PM computing the reverse of a string. So there are 4 possibilities. In the left hand side, I might have A or B, and in the right hand side also, I might have A or B. So left hand side A, right hand side A or B, left hand side B, right hand side A or B. So there could be 4 different possibilities, and we have to handle all these possibilities. 4 options could be there, and we have to take care of all these options. So this is the main thing in this reverse function, taking care of all these 4 possibilities. So Q0 to Q1 blank are as usual. Upper branch when I start with A, bottom branch when I start with B from Q1. Whatever we do for A, replica will be for B, the bottom branch. Let's see what we do in state Q1. Leftmost symbol is A. So we take the first possibility when the leftmost symbol is A, and then we'll go to the appropriate position and see what the rightmost symbol is. So if leftmost is A, in the rightmost position, we have to write A there. So if it is already A, we'll overwrite that, we'll keep that A. If that is B, we'll replace with A. And if that is already A, because left hand side is A, actually we don't need to swap anything. But if that is B, then we have to write A there, come back once again over here, and then write B over here. That is how we swap A and B. So left hand side is A, state is Q1, is a marker because we start from the extreme and then move towards the center. We start with the extreme position, swap last two symbols, then the second left, second right, and so on and so forth. So eventually we'll come to the center. So state is Q1, leftmost symbol is A. The symbol we are considering in the current iteration. For iteration, we swap two symbols. I mean, we swap this symbol with the rightmost symbol and bring back that rightmost symbol over here. That is what we process in an iteration. In an iteration, that is what we process. So Q1 to Q2, it is AR. Then the remaining symbols in between in the state Q2, we skip small a r, small b r, and for the first time I'll get blank because after my input I have infinite number of blanks, and when I continue moving towards right in the state Q2, I'll reach one of those infinite blanks. In fact, the leftmost of those infinite blanks. So first time I'll get blank, and then second iteration onwards, what we do, we swap two symbols and convert into uppercase version and move towards center. So second iteration onwards, we'll find either capital A or capital B in the right hand side. So in the state Q2, the moves are blank blank L. That is for the first time. Subsequently, AL, BBL, those are capitals, and go to the state Q3. And in the Q3 state, we handle those two options. The rightmost symbol is A or the rightmost symbol is B. State is Q3. The rightmost symbol is either small a or small b. Only these two options are possible. Leftmost or small a, rightmost could be either small a or small b. So in the Q3 state, if it is rightmost symbol is small a, I go to Q6 state. When I reach Q6 state, the meaning is the rightmost symbol is A. If I reach Q7 state, then the rightmost symbol is B. That is a junction. Q6 is it's a junction for rightmost A symbol, and Q7 is a junction for having rightmost B symbol. So let's see the first option, left side A, right side A. So in the state Q3, I'll find small a in the right hand side. So I'll write capital A there because left hand side small a was there. So I have to write that A over here. So I have found incidentally A. So as a marker, I'll convert into capital A. I have already converted the leftmost A in the state Q1 into capital A. So basically swapped A with A or maintained A with A. Maintain A is in the leftmost position and the rightmost position. So that is my first option. Going to the state Q6. In case I find B in the right, because I have started with A in the left, I'm now finding B in the right, I have to replace this B with A. And also remember that the rightmost symbol was B because I have to take that B towards the appropriate position in the left. So I go to state Q7. That is my memory that the rightmost symbol was B. So in that case, I replace B with capital A and go to L, start moving towards left. Similarly, the third option, that is the bottom branch, Q1, Q4, that particular branch. Leftmost side is B. Finally, I reach Q5 stage. In the right hand side, I will find either B or A. So those are options 3 and 4, possibilities 3 and 4. Right hand side, if I find B, left hand side B was already there in the state Q1. So because left hand side B was there in the state Q5, I'll replace the rightmost B with capital B because both the sides B's are there. So in fact, we don't need to interchange anything. I'll convert it into capital B and L is the movement. And in case I find A in the right hand side, then my junction for having A in the right hand side, having found A in the right hand side is Q6. So if A is there, because left hand side B was there, I'll replace that A with capital B, L is the displacement, and go to the state Q6. So we have handled all the 4 possibilities. Q6 means right hand side A, Q7 means right hand side B. In the bottom in the bottom branch, it means left hand side B. Top branch means left hand side A. So in the Q6 state, now I'll keep small a's and small b's. For iteration, I convert two letters into capital A, also swap them, and then move towards the center. So my central symbols are all small case letters. Right hand side and the left hand side, leftmost and the rightmost symbols are capital symbols that have been swept. So in the Q6 state, I'll have small a's and small b's. They are not yet swept. So Q6, AL, BBL in the same state Q6. And when I get a capital A or capital B, if I am coming from Q6, coming from Q6 means right hand side A was there. So when I get capital A or capital B, either case, I'll replace that with capital A. This AR, BAR, and go back to the state Q1. Similarly, if I am coming from Q7, it means the right hand side I have found B. So whether I find small a or small b, moving from Q7 to Q1, the bottom arrow, whether I find capital A or capital B, I'll replace that with capital B. And again, prepare myself for the next iteration. It means reach state Q1. So I have converted those extreme symbols into the uppercase version, swept them, moving towards the center. Ultimately, let us take the first case when my string is even in length. So in the state Q1, there won't be any small case letter left now. After I have swept everything, this is the case of even length string. State is Q1. Everything will be the capital letter. And because of the R displacement, I'll be moving towards right and at the center, in fact, at the beginning of the second half. So what I do in the state Q1, I continue moving towards right. It is Q1 to Q8. It is Q1 to Q8. That is this one, bottom line. Q1 to Q8. In the state Q1, no more small case letter I will find because everything we have swept. So whether it is capital A or capital B, I don't change that. Go to state Q8 and continue moving towards right in the state Q8. So it is AR, BBR. And then because of this continuous right movement, finally I'll reach the first blank among the infinite number of blanks which are present. That is after my input. Input I have already processed. I have already swept them. I have already converted them into the capital letters. My state will be Q8. The reason for going to the first blank after my converted or the swept input is that now I'll start returning back and convert this capital letter into the small case letter. Because after I swept, I don't want the capital letters. I only want the small case letters. Reverse of X is also element of sigma star. It is small case letter. Those capital A's are my marker symbols. Those are additional symbols which are there in the tape alphabet. Those are not part of my input. My inputs are when it is capital A means it is small a. The reverse string capital B I have to convert it to small b. So that is AR BBR. State is Q2, Q8, and when I get blank, I go to state Q9. And in the state Q9, again, this was in the state Q8, it was AR BBR, so I'll get the blank. So Q8 to Q9, that's the first blank after the capital letters of the reverse string, so that is blank blank there. In the Q9 state, while moving towards left, I convert all those capital letters into the equivalent small case letters. So if it is capital A, then the reverse string, in the answer, it has to be small a. Similarly, it is capital B, then in the answer it is small b. So it is A, L, capital A, small a, L, capital B, small b, L. The state is Q9. And because of the L displacement, eventually I'll reach cell number 0 where I will stop. That is my halting state. That is the state HA. When I get blank, I go to the halting stage. So this is the case of my string being even in length. Q1 to Q8 to Q9 to HS stage. Now the second case, my string is odd in length. So there the branch will be now that odd. Per iteration we swap two symbols, and in this case the string is odd in length. So eventually my center symbol will be either small a or small b. Remaining I have swapped and converted into capital letters. Finally, Either small a will be left or capital B will be left. So in the state Q1, if the middle unmatched symbol is small a, I'll convert that into capital A. R is the displacement. Then small a, capital A, R is the displacement. And because of this AL, BBL, I'll reach to the state Q3. And in the state Q3 again, I'll continue moving towards right, AR, BBR, AR, BBR, and follow the same process. What is that? In the state Q1, unmatched symbol will be A. That's the additional symbol. String is odd in length. Everything else is capital. It is in capital letter. So Q1 to Q2, R is the displacement. It means when I reach state Q2, I am to the first symbol in the second half, which could be either A or B. Anything could be there. So that is AL, BBL. And finally, in the state Q3, when I get capital A, it is AR. Same logic. AR, when I get capital A, then Q3 to Q8, because this is the capital A symbol which was there. And in the state, if that unmatched symbol is B, then Q1 to Q4, that B, so that is capital B. R is the displacement, where I will find either capital A or capital B. Because of L displacement, I will be back over that center symbol, which must be capital B. So that is BBR, and again going to the state Q8. What is that? State is Q1, unmatched symbol is small a. That is the case. That is made capital A. R is the displacement. So I am in the first symbol in the second half. In the state Q2, here I will find either capital A or capital B. Whether it is A or B, I am making the displacement. So I am going back to that center symbol in the state Q3. That center symbol will be capital A. We know that. We are coming from the upper branch. So that center symbol again AAR. So I'm going back to the next. I'm going back to the next symbol, which is the beginning of the second half. I continue moving towards right. Same logic. In the state Q8, I continue moving towards right. Go to the first blank. Then while moving towards left, I convert all uppercase letters into the lowercase letters. So same Q8, it is Q2, Q3. In the Q3, definitely I'll get capital A, because that was small a found in the state Q1. So that is only AR. I don't need to write BBR. There is no need to write BBR. Similarly, if the middle symbol was small b in the state Q1, eventually in the state Q5, I'll get capital B. R is the displacement. I'll continue moving to the first blank after my capital letters of the reverse string. And in the state Q8, once I get blank, I'll convert all capital letters into the small case letters. Already the string is reversed, and go to the halting state. So Q1, Q2, Q3, Q8, Q9, HA, Q4. Sorry, Q1, Q2, Q3, Q8, Q9, HA. That is my part number 1. Path number 1 for odd length string. When the center symbol is B, my path is Q1, then Q4, Q1, Q4, Q5, Q8, Q9, HA. When the middle symbol is B, small b. When the middle symbol is small a, it is Q1 to Q2 to Q3 to Q8 to Q9 to HA. Only possibility that remains is the string which I am reversing is null. Here that will be represented as blank. So that is Q0 to Q1, blank blank R, and Q1 to the directly to the halting state, blank blank L. Blank blank R means I'm going to cell number 1. Then the blank will be found because my input is blank. So I'll do blank blank L, again return to cell number 0 at the time of halting. So blank blank R, blank blank L, so return to cell number 0 and halt. So that is when my string is blank. That is null. My string is null. Here we'll represent using blank. My string is blank. So that is Q0, Q1, HA. So this is TM4 reversing a string. This is the TM4 reversing a string. I've done execution trace. My input is A double B. The reverse string is BBA capital, and then that is converted into small BBA at the time of halting. That is ABB becomes BBA. perform more execution trace for BA, and finally I'll get AB at the time of halting. The last configuration, HA blank AB. At the time of halting, the position of the read-write head should be over cell number 0, that is over that blank. So that is being achieved. You can verify that later. You may verify that later. Is this fine? Reverse. Is that clear, students? Your feedback?
Yes, sir.
Anyone? Okay. So next is a TM for deleting a symbol. A TM for deleting a symbol. This is the problem statement. Initial configuration is Q0YAZ. Turing machine T that we want to compute, Turing machine T that we want to construct, and at the time of halting, that is the halting with acceptance, that is HA state, my output has to be YZ. So basically, the symbol is A belongs to sigma, that A is to be deleted. Initial configuration is Q0 YAZ. Position of the head is over the symbol that is to be deleted. So we have to delete that. Not only that, you have to pack that. You have to shift Z to the left by one position, that is YZ. And the position of the head should be over the first symbol in the string Z. That's the meaning of underscore below Z. That's the meaning. So we have to delete A basically. A belongs to sigma. It could be blank also. A belongs to sigma union blank. The symbol that is to be deleted is A. A could be a symbol or could be a blank. Initial configuration is Q0YAZ. TM is to be constructed. At the time of halting, the output has to be YZ. Position of the head should be over the first symbol in the string Z. Now Y could be any string. There are two strings. One is Y, other is Z. So Y could be any string over sigma union blank. Any combination of sigma and blank. It means it can contain alphabets. It can also contain blanks. It can have embedded blanks. Sigma union blank whole star. Something like A double B blank B A, anything can be there. Y can be anything. We don't care about Y actually. We don't disturb Y. We delete A and then shift Z to the left by one cell. Y could be anything. But then there is a constraint on Z. Z does not contain embedded blank. Z belongs to sigma star. It could be only blank or it could be non-blank symbols. It cannot contain blank in between. Z belongs to sigma star. This is given. This is part of the problem statement. You have to delete A, shift Z to the left by one cell. Z could be either blank or it contains only non-blank symbols. Y, a string which is to the left of A, can be any symbol, any combination of my symbols in sigma plus blank, any combination of that. But we don't disturb, anyway, we are not disturbing that, so we don't need to worry about that. So this is problem statement, deleting a symbol, constructing a TM for deleting a symbol. And here, unlike all other examples, in the state Q0, my first move is A blank R, B blank R. This is a different move. In all previous examples, the move was blank blank R. See here, Q0 to Q1, blank blank R. Because the input format was blank X. The input string started from cell number 1. Whereas here, we start with a symbol that is to be deleted. YAZ, position of the head is somewhere in center or the symbol that is to be deleted. So in the first step itself, we delete A. What is our logic? We delete A, go to first blank after Z and then shift Z by one cell to pack Z to get YZ. The hole is created. To pack that hole, we'll shift Z by left by one cell. So we go to the first blank after Z and then push Z towards left. So it will give me YZ at the time of halting. So that's the idea. Therefore, the first move is A blank R, B blank R. If it is only blank, my symbol that is to be deleted could be blank also, because A belongs to sigma union blank, could be blank also. So we delete A or B, whatever is there. If it is blank, that we replace blank with blank and go to R. So we have already deleted the symbol that is to be deleted. Now we have reached Q1 state. So what we do? We skip Z. So in the state Q1, it is AR, BBR, we skip Z and go to the first blank after Z. So that is my blank in the state Q1, blank blank L. So we go to the last symbol in the string Z, and my current state is Q blank. Now what we do? Now we want to push Z to the left by one cell so that the hole was created by deleting the symbol A. I have to fill that. So I'm pushing Z to the left. So I'm basically pushing Z from the right end. I go to the rightmost symbol in the Z. So what I do, I'll read that symbol, I'll remember that symbol, and I will delete that symbol. Because that symbol is to be deleted and copied to the symbol to its left. Copy to be copied over the symbol to its left. So what do I do? I delete the symbol. Not only that, I have to remember the symbol because I have to copy that in its left position. So how my current state is Q blank. Suppose currently I am dealing with symbol A, then I'll delete that. And remember that I have deleted A by going to the state QA. Because that A I'll copy to the next row. I am shifting Z to the left by one cell. So in the state Q blank, I'll read the symbol, I delete it at the same time I'll remember that. So A blank L, I go to the state QA, and if I go to state QA, it means if I am in the state Q, it means I have deleted A. If I am in the state QB, it means I have deleted B because I have to take that to its left. So in the state QA, if I get A, then I'll copy A. The state QA is AAL, and I'll remain in the state QA because I have to copy A in the next position. In case I get B, then also I'll replace that with A. This particular arrow between QA to QB. If I get in the state QA, whether I get A or B, I'll write A because I am in the state QA because I had deleted A previously. Once I reach QA, my first thing would be copy A there. So whether I get A or B, I'll write A. Now if I am getting A in the current position where I have already written A, then I'll remain in the state QA because in the next step I have to write A. In case I get B, then I have to write A because I'm in the state QA. If I get B, first thing is to write A and then go to the state QB so that in the next move I'll write B. If I'm in the state QA, it means previously I had deleted A. If I am in the state QB, it means previously I had deleted B. So in the next step I'll write B in the state QB. In the state Q I'll write A. So this I'll form a loop between QA and QB. What symbol I am erasing? If I am erasing A, I'll stay in the state QA. If I am erasing B, I'll stay in the state QB. So from QA, if I get B, then I'll write A and go to state QB. In QB, if I get A, I'll write B, that is ABL, and go to the state QA. So eventually, so while moving right towards left, what I do, I delete a symbol, I remember a symbol, then copy in the next position. Also remember what I have erased in that position because in the next cell I have to write that symbol. So eventually I am shifting Z by one position. Finally, I'll reach to the blank cell created by deleting this particular symbol. It's YAZ. I have deleted that. I have removed that. I replaced A with blank. So that was my first move, Q0 to Q1, A blank R, B blank R. So I have made a hole. I have erased A and B and replaced with blank. So in the state QA, when I get blank, it means I have reached to that location. And because I had previously deleted A, that is the reason I am in the state QA. I'll write there A. And S is displacement. My head will be positioned over the first symbol in Z. Similarly, if I am coming from QB state, when I get blank, I'll go to the halting state and write B there. That is the blank created by deleting that particular symbol, the first symbol, right? Symbol YAZ, that particular A. If I get blank in the state QB, I'll write B at the time of halting. If I am coming from QA state, I'll write A there and hold. In case my string is my string Z is only blank. I won't find any A's and B's. I won't find B. Symbol A That is A blank R, B blank R, blank blank R. So I go to Z, and in case Z is blank, so in the state Q1 I'll find blank. So that is blank blank L, that is blank blank L, and in the Q blank state I'll move to the halting state with blank blank S. With Q blank to HA blank blank S. So this is the case when my Z string is blank, when it is blank. So this is a TM for deleting a symbol. So we are computing a function. We have implemented the delete function. Previously we had implemented the reverse function. We had implemented the copy function. We had implemented the mod function. Is that clear, students?
Yes,
Okay,
sir.
you can see the execution trace later. It's something like AABB. That is the string. So position of the head initially is or the character that is to be deleted. So my output has to be A. My string Z here is BB. So at the time of halting, the position of the head should be over the first B. So we start by deleting this particular A. You look at Q1, we delete A. So A blank output A double B, the position of head, the leftmost.
Sir, you're cutting off.
Anyway, let me try out just a minute. Is it better? Is it better now?
Yes, sir.
So that was my Y is A in this example. Symbol that is to be deleted is A. That is position over that. My string is Z, which is BB. Output is A double B. Position of the head should be over the B, first B, leftmost B, and that is what we achieve. Next, implementing what is called the characteristic function of a set. Defined like this. Implementing the characteristic function, TM to implement the characteristic function of a set. Here is the definition. Meaning of a characteristic function is given to you. What is that? Just look at that. Output is 1 or 0. Basically, it cannot be crash. Explicit 0 and 1 output is to be generated. That is the meaning of implementing a characteristic function. 0 or 1 is the required output. Look at that. Excel is my characteristic function of a language L, which is a mapping from sigma star to 0, 1. It means take a string X that belongs to sigma star. Output is 1 if X belongs to L, else 0. Excel is the characteristic function of a language or a set, which is a mapping from sigma star to 0, 1. It means take a string in sigma star and generate output either 0 or 1 explicitly as per this definition. Excel capital X LX equal to curly bracket 1 or 0. If X belongs to L, the output has to be 1, otherwise 0. So explicit 0 output is also to be required to be generated. Here that crash won't work. You have to generate specifically output 1 or 0 at the time of halting. At the time of halting, the specific output is generated. That is the meaning of the characteristic function of a language or a set. The characteristic function of a language or a set. A language is nothing but a set. Fine. So this is palindrome. Same example, same logic. Same logic. Minor changes. Minor changes. I think this you remember our Turing machine for accepting the language of palindrome. Let me see if I, yeah, this one. TM4 accepting the language of palindrome. We match extreme two symbols, and if they match, we make them blank and move towards the center. This Q1, Q2, Q3, Q4, that is matching leftmost A with rightmost A, making them blank, and then moving towards the center. Whatever match, we make blank and move to the center. So in the ultimately in the state Q1, if my string is an even length palindrome, will be in the state Q1, everything will be blank, go to the holding state. If it is an odd length palindrome, then in the Q3 state, if the middle symbol is A, will be in the Q3 state. If the middle symbol is B, will be in the Q6 state. And again, we hold. You already made the single unmatched character into blank Q1 to Q2 for A, Q1 to Q5 for B. So that is palindrome, the language of palindrome. TM4, except in the language of palindrome, this was the TM. But then we didn't generate explicit output 1 or 0. So when we want to compute characteristic function for the language of palindrome, we must explicitly generate output 1 and 0 respectively, depends whether the string is a palindrome or not. The palindrome output is 1, else it is 0. Blank 1, blank 0. That output is required. So we make certain changes. The basic structure remains the same. Q1, Q2, Q3, Q4, Q6, Q5, that structure remains the same. Now, let us take the case of, okay. This is Q0 to Q1. My first move is blank AR. So on cell number 0, what I'm doing? Writing small a there. That is my marker symbol. The matching symbols, the matching starts from cell number 1. My input begins from cell number 1. So first cell and the last cell content, when they match, we make it blank. So matching things are made blank, and eventually everything will be blank except the content of cell number 0, because here explicitly I have written A. It is blank AR, Q0 to Q1, blank small AR. This small a which I am writing on cell number 0, that is my marker symbol. Because when everything is blank, when I continue moving towards left, finally I will reach cell number 0. And if that content is A, I know that everything has matched, and there, this is my cell number 0. This is a marker for cell number 0. So I'll make that particular symbol blank, go to cell number 1 and write there 1, because this is a palindrome. Required output is blank 1. Required output is blank 1. So that is my marker symbol. Even better is, instead of small a, I'm writing hash. So I don't worry about A's and B's, which are there part of my input. So I replace blank with hash. Content of cell number 0 is, I put hash there. I put hash there. Remaining logic same. Now coming from Q1, when everything is matched, this is the case of my even length palindrome. In the state Q1, what I'm doing? Blank blank L, and because as per the previous logic I have written small a over cell number 0. So in the state Q1, Q7, I'll find there A. So A blank R, or make content of cell number 0 blank. Go to state Q8. In the state Q8, I'll find a blank because everything has matched except content of cell number 0, which is my marker symbol, which was my marker symbol A. I have already converted that into blank. My required output is blank 1, and because of R displacement, I am over cell number 1. There I write 1, and L is the displacement, so go back to cell number 0 and hold. So I have explicitly generated output blank 1. This is the case of even length palindrome. Coming from Q1, that is even length palindrome. Coming from Q3, Q6, that is the case of odd length palindrome. Again, Q3, Q6, same logic, blank blank L. Everything has matched. And same logic, we connect to Q7, blank blank L. I find A, that's the content of cell number 0, make it blank and accept it, and write explicitly blank 1. So Q3, Q6, this is the case of odd length palindrome. The unmatched middle symbol is already made blank over here. Q1 to Q2, A blank R. This is the unmatched additional symbol. Everything else has matched. That becomes blank. Coming from Q3, now everything is blank except the content of cell number 0, where I had written either small a or hash. as a marker that that is my cell number 0, because the QM does not recognize these cells by numbers. So Q3 state blank blank L, and again I'm writing explicitly output as blank 1. This was the case of odd length palindrome. Now comes the third case, non-palindrome. This is the characteristic function, so I have to explicitly generate output as 0 or 1. 0 or 1. So in the state Q3, if I find B, in the state Q1 I have started with A. In the state Q3, if I find B in the right hand side, we know this is not a palindrome. This is not a palindrome. This is the case of non-palindrome. Similarly, Q1, if I start with B in the left, and in the Q6 state, if I find A, Q6 state I find A, then I know again this is not a palindrome. Starting with A and getting B, starting with B and getting A in the corresponding position. These are non-palindrome spaces. So that is Q3, Q6, getting B or getting A, we go to Q9. This is a case of non-palindrome. And in between, once I have one extreme A, the corresponding extreme B or vice versa, in between are non-match symbols. But these are non-blank symbols because they are not matched. We don't have, there's no need to match them. So in the state Q9, what I do, A blank L, B blank L. In between, I now make them blank. This is non-palindrome. State is Q9 and A blank L, B blank L. Then in the state Q9, I'll get blank. The symbols that have matched from the left hand side and corresponding from the right hand side, symbols that have matched are blank. Then I get a pair which is not matching. In between those non-blank symbols, I don't need to match. I convert directly into blanks. The symbols to the left of the leftmost symbol and to the right of the rightmost symbol all are blank because they have already been matched. So in the Q1, in the Q10 state, it's blank blank L. Q9 state, I get a blank and then continue moving towards left, it is blank blank L. Finally, I'll get A. It means that is my cell number 0. I make that blank, go to cell number 1, that's the R displacement, write there 0. Take is Q11, write 0 in the content, that particular blank, and again go to cell number 0, as L is the displacement. So my output here is blank 0. This is explicitly generating 0 output or 1 output. That is the meaning of characteristic function. Implementing a characteristic function means explicitly generating 0 or 1 output as per the definition. So here we are generating 1 in the case of palindrome and non-palindrome coming from Q3, Q6 with non-matching symbols Q9, Q10, Q11 and writing 0. Even slightly we can optimize this Q9, Q10, Q11 by writing blank hash R. So there, because we have written A blank L, B blank L, then blank blank L to Q10, then blank blank L, and then A blank, Q9 and Q10, now we can combine. If you have written hash over cell number 0, because here in the initial part we have written A, so we don't know this A can merge with blank, so we have written Q9 and Q10 separate states. But if you have written hash on cell number 0 at the beginning, instead of blank R, if you had written blank hash R, then we can merge Q9, Q10. We can merge Q9, Q10, something like that. Q9, Q10. Q9 is A blank L, B blank L, blank blank L. Now don't worry. We don't need to worry of crossing the 0th cell. Here in the previous case, we need to take care that we don't go to the left of the 0th cell. Here, there is no possibility of crossing that border because hash is my cushion. And when I get hash, I know I have reached cell number 0. So I make that blank. R is the displacement. So we go to cell number 1, write there 0, and go return to cell number 0. That is blank 0 L. So that's the benefit of putting a symbol other than our sigma symbol here. Between Q0 to Q1, here we have put hash. We can merge Q9, Q10. Accordingly, the moves will be even between Q1, Q8, HA, Q1, Q8, HA. We can merge these states also. Q7, Q8 can be merged. So that is blank blank L. Again in Q7, Q8, we move towards L. One blank blank L, and once getting hash, we go to Q8 state directly. We go to Q8 state directly. So fine. So that's the implementing the characteristic function. Any doubt? Is that clear? Waiting for your response. Yes or no?
Yes, sir.
Okay.
So characteristic function basically returns 1 if the Turing
Yes,
machine
yes,
is accepting the
yes.
input, right?
Yeah, this is the definition. This one.
Yeah.
X belongs to L. Output
Yes,
is
sir.
1.
Got it. Thank you, sir.
1 or 0. Explicit output is required. Blank 1 or blank 0. That will be the output of Turing machine. Depends upon whether X belongs to L or not.
So what do you mean by blank 0 and blank 1?
No, that's blank 0 means content of cell number 0 is blank.
Okay.
And from cell number 1, we have written 0. Normally,
Okay,
we keep cell number 0, the leftmost cell as blank. Usually, we keep that blank.
Okay,
This is
sir.
blank 0, and the position of the head is over that particular blank. That is over the leftmost cell.
Okay, sir. Thank you, sir.
I think one of the previous, yeah, this one. Rightmost blank, blank 1 or blank 1, 1. So that's the content of, this is content of cell number 0, blank. This is content of cell number 0 and 1, remainder is 1. That is blank 1. And content of cell number 0, 1 and 2, blank 1, 1. Position of the head is to the right of this second one, or we have infinite number of blanks. By default, the content of each cell is blank. These are the specific contents of cell 0, cell 1, cell 2 respectively. Remainder is 2. Content of cell 0 is blank, cell 1 is 1, cell 2 is 1. And the position of the head is over cell number 0. That is meaning of underscore. Is that fine? Yes
Yes,
or
sir.
no?
Yes, sir.
Next we take, I think we can have a break of 10 minutes maximum, and we continue from this composite Turing machine. This is a theorem we will not discuss. I'll just give you a very 2-3 minute idea about that. We'll not discuss. We won't look into the proof. Right? So we can have 5-7 minutes break, and after the break we continue with the next example, that is composite Turing machine or cascading of Turing machines. We stop here for 8 to 10 minutes.
This meeting is being recorded.
Okay, so we go to the next topic, which is composite Turing machine or combining Turing machines. Or
Sir, I have a
cascading.
doubt, sir.
Your doubt, yeah.
Like we will do just till chapter 7.3, right? I mean till 7.3 part.
Till whatever is discussed by today's end of the lecture.
Okay, sir. And what will be the weightage of the LCM, sir?
50%. Weightage we are not changing.
Okay, thank you, sir.
50 marks, 50% weightage.
Okay, thank you.
14, 18, 18.
Thank you, sir.
Composite Turing machine, which is combining of Turing machines. So output of one Turing machine at the time of vaulting, that is connected to the input of the second Turing machine.
Excuse me, sir.
Yeah,
So you say the weightage is 50%.
yeah.
Okay, fine. Thanks.
40, 10, 50. We are not changing that. With same 40, your assignment 10 and 50 answer. So output of T1 is connected to the input of T2 at the time of vaulting, and the notation is T1. If it is vaulting with A, then T1 to T2 is vaulting with A. In general, equal to T1 T2 dash T2. So when T1 holds, output has to be A. If that is the case, then it is represented like this. In general, halting moves of T1 are redirected to the initial state of T2. The halting state of T1 is removed. It is removed. These halting moves are redirected to the initial state of T2, and the halting state of T1, that is removed. T holds only if T2 holds. So basically the control is with the T2, its halting state. T holds only if T2 holds. If T1 or T2 loops or crash, then so does T. If T1 or T2 loops or crash, then so does T. Only when T2 holds, T holds. When the halting moves are redirected to the initial state of T2, the halting state of T1 is removed. So that is composite Turing machine T1, T2, that is my T. Example is this one. Example of a composite Turing machine. Input is blank X. And we have a sub-Turing machines named copy, reverse, equal in this composite Turing machine. This is my composite Turing machine. Wherever copy is written, there is a one Turing machine. Reverse is our reverse, already we have discussed with a specification like this. And third one is equal. This is my composite Turing machine comprising of sub Turing machines named copy, reverse, and equal. There are three Turing machines or three sub Turing machines named copy, reverse, and equal. T1, T2, T3 basically. So how it works? Say Q0, I'm providing my input on blank. So to copy, my input will be blank X. That is the meaning of notation this blank. That is the initial content here. Copy. So copy is output is blank X, blank X. Output of copy will be something like blank X, blank X. That is terminated. Halting move of Q1 is terminated at Q1. So at Q1, this will be my blank X, blank X. Blank blank R, I'm going to Q2. My first X, I'm skipping, that is ARBBR. After it, there is a blank. On that blank, I'm going to the reverse. I'm going to the reverse. So input to the reverse is something like blank X, blank X. Position of that blank is over the second blank from left after X, after first X. And output of that reverse is this blank X is reversed. Already we have discussed the reverse. So that becomes blank XR means X raised to R means reverse of X. So that is blank X reverse. It is terminated. The reverse move or the reverse sub-Turing machine halting move is terminated at Q3. So that is blank XR. In Q3 we go to blank L. So now we are moving towards left. We skip X. So that is ALBBL. Go to cell number 0 and then apply this on blank to equal. Now this X and X reverse are same. Then output of equal is 1, otherwise equal is 0. Otherwise, this is 0. So this is composite Turing machine for nothing but palindrome. X is there. We compute reverse. We copy that X. So that blank X becomes blank X, blank X. Then that second blank X, we reverse that. Then we match X with reverse of X. That is my equal. Matching equal is matching first string with the second, matching first string with the second string after reversing that. Output of equal, if that is 1, then it is a palindrome, otherwise not. So this is a second way of implementing palindrome. Already we have constructed a TM. This is the second way of constructing a composite Turing machine for accepting the language of palindrome. So if you can see this equal blank x blank y, if x and y are same, output is 1, otherwise 0. Blank 1 or blank 0. Output is blank 1 or blank 0. Output is 1 or 0. 1 is written on cell number 1, 0 is written on cell number 1. Output is 1 or 0 or blank 1, blank 0. If x equal to y, otherwise not equal, output is 0, blank 0. So that is equal. Reverse, input has to be blank x, output is blank xr. Copy, blank x, blank x, blank x. So that is my composite Turing machine. Copy will give me blank x with this position of the retrieved head, and then I give that to reverse, so it will give me blank x blank xr as the output. Then I give that to equal, and then x and xr are matched. If they are matching, it's a palindrome. Output is 1, else output is 0. Output is 1 or 0. 1 or 0. We say it blank 1 or blank 0. 1 is written on cell number 1, and so is 0 written. Output is 1 or 0. This is palindrome. This is an example of a cascading of Turing machine or composite Turing machine. We combine more than one Turing machine. Universal Turing machine. So actually this is an important concept, very important concept. We'll not look at the theorem. But a lot of syllabus is there, so we'll not look at the theorem. Turing machine means, see, so far whatever we have done, it was for either accepting one language. We have constructed a TM for accepting one language or computing one function. We claim that a TM Turing machine is a general model of computation, and general computer can do only whatever the Turing machine can do. A general purpose computer is no more powerful than a Turing machine. It's a general model of computation, Turing machine. Then if it is accepting only one language or computing one function, how can we claim that it is a general model of computation? Answer to that was given by Turing in terms of what is called universal Turing machine. Universal Turing machine, TU. Input to TU is universal Turing machine, TU. Input to Turing machine, TU is a Turing machine and a string. And whatever is the result of simulating moves of T or string Z will be the output of TU. In short, a TU can execute moves of any Turing machine. When we say Turing machine, it is like an algorithm. It can execute any algorithm. That is what a general purpose computer can do. So here TU can execute moves of any Turing machine. So that's the name universal Turing machine, only for the knowledge. These examples in the theorem itself will take, I think 1.5 hours for this. We don't discuss that. This was universal Turing machine with proof. Please keep that. Next is the fine. So this only for the concept, that's fine. What does a TU do? That's fine, only up to that information. Now, non-deterministic Turing machine. We said that a non-deterministic Turing machine is same powerful as a deterministic Turing machine. It's not more powerful than a deterministic Turing machine. Unlike a PDA. A non-deterministic PDA is more powerful than deterministic PDA. Finite automata, non-deterministic and deterministic, same power. In fact, we can convert any NFNL to FA. We can convert any NFA or NFNL to FA. There is no question of more powerful. So first and the third model of computation, same power. Central, PDA. Non-deterministic PDA is more powerful than a deterministic PDA. So here is an example of a non-deterministic Turing machine for accepting the strings of length 2 raised to I. 2 raised to I. Just look into that. Again, there is a very important theorem on non-deterministic Turing machine. whatever as a non-deterministic Turing machine can do, a deterministic Turing machine also can do the same thing. But that theorem we will not discuss. Take example of this non-deterministic Turing machine. Let's see how it works. Blank blank R, 1 1 R, then blank blank R, state is Q2. So this is my input. See, blank blank R, then my input begins. Blank blank R means I'm going to cell number 1, and it is 1 1 R. So that is my input. After that input, there is a blank. State is Q2. I'm skipping that blank and reaching Q2, and on the next blank I am writing 1, and then executing this double. Double is once again a sub-Turing machine. A double is a sub-Turing machine which will double my input, which will double my numerical input. So it's similar to copy, but the difference is copy works with the strings. Here double works with numerical inputs. Difference number 1. And second, in the case of copy, there is something like blank x as the input, and output is blank x, blank x. So there is a gap. There is one blank between input and output. It is x, blank x. My input is x, then there is a blank, and there is x. Whereas in the case of double, that blank is not left. That is not kept. So if my input is 1 1, output will be 1 1 1 1. No gap between these two ones. My input is say 3 ones, output will be 6 ones without any separating blank. So that is how double works. Modified copy for one symbol input alphabet. Let's make a copy of the numerical input. It then release the blank separating the original input from the copy and returns stated to the square 0. So that is what we say. In short, it doubles the value of the input without a separating blank. That is the functionality of double sub-Turing machine. So what is happening in state Q2? I am writing 1, and then in the state Q3 I am executing this double. I may not execute at all. I can take a branch Q2, Q3, Q4 without looking. So what happens? I am actually comparing my input with 1. See, state Q2 to Q3. My input is in the state Q1. I am skipping all those inputs. Then there is a blank which I am skipping. On the second blank, or from the second blank, I am writing 1, blank 1L, Q2 to Q3. So I am first writing 1. And then let us discard this double. Time being, let us say we are not executing this double. So Q3 to Q4, I'll take blank blank L. Then I'll skip 1 1L. Basically, I'm skipping input. So there is an input. After input, I am writing blank. I'm keeping 1 blank, and on the next blank, I'm writing 1. So input, blank, and 1 initially. And then I am going back to the input while moving towards left. And then I'm going to cell number 0, I'm executing equal sub-Turing machine. So what I'm saying, I'm comparing input with single 1 initially. 1 means 2 raised to 0. In case they don't match, then this is a non-deterministic Turing machine. In the state Q3, I'll come back and I'll execute double. So that single 1 which I had written in the state Q2 to Q3, I have written single 1. I'll double that. So single 1 becomes double 1. So that is 2 raised to 1. If I execute one more number of times that double, that becomes 2 square. That becomes 2 cube. So as I go on executing this double, I go on iterating this double for one more number of times. So basically I'm having 2 raised to 1, 2 raised to 2, 2 raised to 3, 2 raised to 4. Basically I'm comparing input with 2 raised to 0. If they don't match, then with 2 raised to 1 by executing this double once. By executing this double twice, I'm comparing with 2 raised to square, 2 raised to 3, 2 raised to 4. So I'm checking whether my input is of the form 2 raised to I or not. And non-deterministic Turing machine for accepting the strings of length 2 raised to I. So eventually, if the input is of 2 raised to I, then some number will come. That number is nothing but that many number of times I am executing double. That is my I. By that, I'll get the same output. Whatever is my input, by executing the double I number of times, I'll have the same out, I have the matching output, and I'll say they are equal. So I'm determining whether my input is of the form 2 raised to I or not by this non-deterministic Turing machine. And the non-determinism lies in how many times I execute double. I can randomly execute double one time, 2 times, 3 times, and because this is non-deterministic, I have the choice of executing this at any number of times. Eventually, I have to correctly execute that correct number of times if my input is of the form 2 raised to I. So that is working of double. This is my non-deterministic Turing machine. And finally, I will correctly execute this double I number of times so that my input will be determined whether it is of the form 2 raised to I or not. If it is not of the form 2 raised to I, then eventually I cannot find any such I. And a TM can go looping indefinitely. In that case, either I will reach a number which will be higher than my first part, or I can even execute this double. I can execute this particular Turing machine indefinite number of times without generating an output. That is also fine. So on the other hand, if the input string is not a power of 2, it will fail to be executed because the last step is to be compared to a string that must be a power of 2. Thus, T accept the language 2 raised to I. And this is unary representation. So 1 raised to 2 raised to I. It is accepting the language 2 raised to I. T accept the language 2 raised to I. If it is of 2 raised to I, if the input string is of the 2 raised to I, then it will be accepted. And this is unary representation. So it is 1 raised to 2 raised to I. If my input is of the 2 raised to 5, output will be 1, not otherwise. So this was non-deterministic Turing machine. This is non-deterministic approach. Non-determinism lies in how many times I execute this double. That is up to my choice. But I have to correctly execute it once if the input is of the type 2 raised to I. Even I can accept this 2 raised to I using a deterministic approach. This was a non-deterministic approach. Deterministic approach would be division. Here, non-deterministic approach, I have used multiplication. I am doubling this. Using a deterministic approach, using division also, I can accept this language. I can construct a TM. Using deterministic approach, it can be solved here. The division will be performed instead of multiplication. Check first if it is 1. If not, then perform a sequence of division by 2. If at step before reaching 1, we get a non-zero remainder, the answer is no. If we finally obtain the quotient 1 without any of the divisions producing a remainder, the answer is yes. Normally, a multiplication by 2 is an easier approach than division. Therefore, we prefer this division approach for accepting language 1 raised to 2 raised to I. Fine. So that was about non-deterministic Turing machine. Once again, NFA-FA, same power in terms of language acceptance. DTM and DTM, same power in terms of language acceptance. DPDA and PDA, NPDA is more powerful. An example is palindrome, cannot be accepted by any deterministic PDA. Palindrome, that is not a DCFR, it is not a deterministic context-free language. This is a non-deterministic context-free language. That word is also used. Fine. So, a deterministic TM is as powerful as a non-deterministic TM, and this is a proof. Actually, this is the most difficult proof in the course. We are not going to discuss that. We are not going to discuss this. That completes the proof. This is part of the proof. Only for concept, deterministic TM and non-deterministic TM are equally powerful. Now, the last part about Turing machine is what is called Church-Turing thesis, and here is the statement. The power of Turing machine was described by the American logician named Church, year 1936, and the statement is any algorithmic procedure that can be carried out by a human, a team of humans, or a computer can also be carried out by a Turing machine. The power of Turing machine was described by American logician Church, year 1936, and that statement is called Church-Turing thesis. The statement is any algorithmic procedure that can be carried out by a human, a team of humans, or a computer can be carried out by a Turing machine. So that describes power of a computer, power of a Turing machine. For a computer to do a task, it requires an algorithm. It requires set of instructions. It requires an algorithm, and any algorithmic procedure that can be carried out either by a human or a group of human or a computer, a TM can do that. So this is not a mathematically precise statement. Above statement is not a mathematically precise statement, and the reason is there is no precise definition for algorithmic procedure. There is no precise definition for algorithmic procedure. But since the invention, enough evidence is found for its correctness, and generally the statement is accepted. Mathematically, of course, we cannot prove it because of above constraint. And the benefit of accepting our statement is that we can say that what is algorithm? Now we can define algorithm. An algorithm is a procedure. The benefit of accepting this has never been contradicted. Therefore, since this has been given, it has never been contradicted. Therefore, it is considered to be correct. And the benefit of accepting this definition is now we can define what is an algorithm. So an algorithm is a procedure that can be executed on a TM. But we can now define what is an algorithm. Accepting above statement, we can now state that an algorithm, what is an algorithm? An algorithm is a procedure that can be executed on a TM. Now we can discuss about the problems that can be solved algorithmically and problems that can't be solved. There's something called halting problem. Again, because of time constraint, we are not going to discuss that. The advantage of the above definition of this algorithm is that now we can discuss about the problems that can be solved algorithmically and problems that can't be solved. If you know those NP complete and NP hard, etc., then it is defined in terms of Turing machine, whether a TM can compute that in a polynomial time or not. So that is the advantage of this definition, the power of the Turing machine, advantage of accepting this definition, and finally we can say about the solvable problems, unsolvable problems based on the Turing machine's definition.
Sir, this constraint, what is the constraint? Mathematically, it can't be proved because of the above constraint.
No, the algorithmic procedure, there's no precise mathematical definition for what is an algorithmic procedure and what is not. No precise mathematical definition for algorithmic procedure is not available.
Okay, sir.
But then whatever the statement is there has always been found to be true, therefore it is accepted, and once we accept that, this is the definition of an algorithm. This is the definition of an algorithm, and then we can talk about the problems that can be solved, problems that can't be solved. Recollect your advanced algorithm concepts, that it is defined in terms of Turing machine. Fine. The last topic is recursively enumerable language. Last topic is recursively enumerable languages. Now we have been using interchangeably the words accepting a language and recognizing the language. Actually, both of them are different. In some literature, you will find this recognizing as deciding a language, accepting a language and deciding or recognizing a language. We'll use the word recognizing a language. So let N be a subset of sigma star. Let N be a subset of sigma star be a language, and a TMT with input alphabet sigma is said to accept L if LT equal to L. And T recognizes or decides L if T computes the characteristic function XL sigma star to 0, 1. When we say recognizable, in the case of acceptable, I mean, there's no need to produce explicit output as 1 and 0. That is the case of acceptance of a language. And when we say it is decidable or recognizable, then it has to implement, it has to compute the characteristic function, which means precisely it has to generate output as 0 and 1. In other words, T recognizes L if T holds in state HA for every string X belongs to sigma star, producing output 1 if X belongs to L and output 0 otherwise. So the TMP is able to recognize L, it means it is generating explicitly output as 1 and 0. In the case of accepting, normally if the string belongs to this, the TM holds, that's it. Except a T with input alphabet sigma is said to accept L if LT equal to L. So it will hold. In the case of recognition, it will generate output. Not only it will hold, but it will generate output 0 and 1. And the language L is recursively enumerable. The language corresponding to TM is called recursively enumerable. Language accepted by TM, that is recursively enumerable. Language L is recursively enumerable if there is a TM that accepts L. For a language, there is a TM which accepts the language, then the language is said to be recursively enumerable. And recursive, language is recursive if there is a TM. I think there is a repeated, there is one sentence repeated, ignore that. And recursive if there is a TM that recognizes L. There is a TM that decides L, then the language is said to be recursive. You will also find words like Turing acceptable or Turing decidable, or accepting and recognizing the language. These are synonyms used in other literature. With that definition, the difference is, the statement is every recursive language is recursively enumerable. A theorem, a statement is every recursive language is recursively enumerable. So how we argue for this statement? Every recursive language is recursively enumerable. Now, if a Turing machine recognizing L, a Turing machine recognizes L, then we can get a TM which accepts L by modifying T so that when it leaves output 0, it enters the reject state. This is very, see, there is a TM which recognizes the language. It means it explicitly generates output 1 and 0. Now we have to claim that it is also recursively enumerable. In that case, the TM has to accept the language. TM has to accept the language. So whenever there is output 0 is being produced by the TM, it will go to the HR stage. It will go to the HR stage. So if a Turing machine recognizes L, that is given every recursive language, means there is a Turing machine which recognizes L, then we can get a TM accepting L. You have to prove that it is recursively enumerable. We can get a TM accepting L by modifying T so that when it leaves output 0, it enters the reject state. If L is accepted by a non-deterministic TM T, and every possible sequence of moves of T causes it to halt, then L is recursive. One more statement. If L is accepted by a non-deterministic TM T, and every possible sequence of moves of T causes it to halt, then L is recursive. Because it is reaching halting state in all the cases. So here we can, I mean, just the logic for that, we are not going to go much deeper into the proof for the statement. For every possible sequence, it is reaching the halting state. So we can generate here output 1 and 0 appropriately. There is no sequence in which no delta QA equal to phi is not occurring. Every sequence is leading to the halting state. So we can generate appropriate output as 1 or 0. Therefore, we can say the language is recursive when L is recursive. This is the logic. If L1 and L2 are recursively enumerable languages or sigma, then L1 and L2 and L1 intersection L2 are also recursively enumerable. It means recursively enumerable languages are closed under union and intersection operations. Union of recursively enumerable languages is recursively enumerable. Similarly, intersection of recursively enumerable languages is a recursively enumerable language. They are closed under union and intersection operation. You may remember this, such a statement we have made for regular languages also. Regular languages also, context-free languages also. Theorem, if L is recursive, so is L dash. If L is recursive, so is L dash. You may remember that complement of a context-free language may or may not be a context-free language. Context-free languages may not be closed, they are not closed under complement operation. Complement of a CFL may or may not be a CFL. Whereas here, if L is recursive, then L dash is also recursive. So complement of a recursive language is recursive. If L is recursive, so is L dash. And proof is very simple. L is recursive. Now we have to show that L dash is recursive. And here is a very simple argument. If T is a Turing machine recognizing L, then we can make it to recognize L dash. We can make it recognize L dash by interchanging the two outputs. So it is given that it is recursive. So there is a Turing machine Recognize this L, so it generates output 1 and 0. Now we have to recognize L dash. So just swap these outputs. We can make it recognize L dash by interchanging the two outputs. So if L is recursive, then L dash is also recursive. So these are some of the statements. We have proved some of them. We have given arguments for some other statement, logical argument for some other statement, and next we define what is called unrestricted grammar. Unrestricted or phase structured grammar is a four tuple V sigma SP. V sigma are disjoint set of variables and terminals, same meaning. S is element of V, called the start symbol, same meaning. P production, same meaning. Only difference is type of the production. Otherwise it is like TFG. This is unrestricted or phase structure grammar. Same tuples, only difference is in the type of productions P have, and every production in P, they are of the form alpha gives me beta, where alpha and beta belongs to V union sigma star, and alpha contains at least one variable. Alpha contains at least one variable. In the case of context-free grammar, what is that? Left hand side, that is alpha means exactly one variable. Right hand side, any combination of terminals and non-terminals, any combination of variables and terminals. Here, left hand side and right hand side both, any combination of variables and terminals. V union sigma star. For both alpha and beta, only difference is, only constraint is alpha must contain one variable. The string alpha must contain one variable. So that is unrestricted or phase structure grammar. Example is this one. A raised to I, that A and B and C n. We didn't have a context-free grammar accepting the language, generating the language A to the power n, B to the power n, C to the power n. That is not a CFN. Therefore, we can't have a CFG. So the same language, now we are writing what is called unrestricted grammar. We are writing unrestricted grammar. And the difference here is left hand side, see I have combination of terminals and non-terminals. Look at these productions. Look at these productions. In the left hand side of the arrow, we have more than one symbol. A combination of terminals and non-terminals. At least one symbol must be a non-terminal, must be a variable. In the case of CFG, left hand side exactly one variable. So we could not generate a language of the form AN, BN, CN. So S gives me F, SN, S gives me F, S1. S1 is ABC, S1 or ABC. BA becomes AB, CA becomes AC, CB becomes BC. I can change this order. BA, because ultimately I want all A's at the beginning. See, S1 gives me ABC, then S1. So again, I have ABC, S1. So ultimately I have ABC, then ABC. But what I require all A's at the beginning, then middle all B's, then all C's. So I have to change the sequence. So in that case, BA becomes AB, CA becomes AC, CB becomes BC. My first A becomes A. Again, there is A and capital A. Then I get two terminals A. Similarly, from AB I can get AB, BB I get BP. From BC I get BC, CC I get CC. So this is unrestricted grammar. This is a product. These are productions of unrestricted grammar. Now you can generate something like A, B, B, C, C. See, let's use me FS1. Then from S1 I am saying ABC S1. From S1 I am saying ABC S1. Then I am changing the sequence. A becomes A can become AC, BA can become AB. So I have all A's at the beginning. Again, CB can become BC. So all A, all BB, all CC, and then I generate those terminals. From A, double A, from AB, AB, from BB, small b, capital B, BB. From B, capital C, it is BC, small. From small c, capital C, it is, and that is how I generate A square, B square, C square. A, BB, CC. And it is taken care that I have equal numbers by generating equal A, equal B, equal C. And then it is compulsory This is the only way I can generate terminals from this combination of terminal and non-terminal. From A I get double A, from AB I get AB. So it is ensured that only after A's I have B's. BB get BB, from BC I get BC. So it's ensured that all A's first, then all B's, then all C. That is only way I can get all terminals. I can derive a string. I can't have something like small a, small b, small c, small a, small b, small c. Cannot derive that. If I'm able to derive that, then this my grammar is not for A and B and C and. It is ensured that I cannot disobey the sequence all A's, all B's, and all C's. So that is how this small a capital A gives me A, and if I want to generate B, small b, then I have to have A before that. So small a capital B gives me AB. So it is taken care, the sequence is taken care, the numbers are taken care over here. The sequence is taken care by these productions. Capital and small combination. Only valid combinations are permitted. Numbers are taken care here. ABC, ABC. This one gives me ABC, ABC. And from this F, I generate A. From this capital F, I generate A. FA. First, from symbol F and then capital A, I generate first A. So this is an example of unrestricted grammar. If for any unrestricted grammar G equal to V sigma SP, there is a Turing machine T with LT equal to LG. So Turing machine corresponding grammar is unrestricted grammar, language is recursively enumerable language. For any recursively enumerable language L, there is an unrestricted grammar G generating the language. For any recursively enumerable language L, there is an unrestricted grammar G generating L. One more definition of context sensitive grammar. This was unrestricted grammar. Context sensitive grammar, only the definition, CSG. Again, all those parameters, alpha gives me beta. Length of beta has to be greater than or equal to length of alpha. Length of beta has to be greater than or equal to length of alpha. That's the requirement for a context sensitive language, CSL. Every context sensitive language is recursive, and not all languages are recursively enumerable. There are some languages which are not recursively enumerable. Not all languages are recursively enumerable. This we have seen. If L1 and L2 are recursive languages, then L1 union L2, L1 intersection L2 are also recursive. And the last part is what is called Chomsky hierarchy. The innermost in the hierarchy, the innermost part of the circle is regular. That is type 3 language or type 3 grammar. That is smallest set, that is my regular language. Above regular language comes type 2 language, which is context free language. More generalized language, they are context sensitive language. You know, C language is not a context free language. I have to declare the variables before I use that. That is one of the examples. There are many concepts which cannot be, every concept of C cannot be generated using context free grammar. It falls into the category actually context sensitive language, and the outermost is what is called recursively enumerable language. The most generalized, that is recursively enumerable, context sensitive, context free, then regular. So this is my Chomsky hierarchy. The categorization, the classification of language given by Chomsky, called Chomsky hierarchy, something like this: type 0, type 1, type 2, type 3. Type 0 recursively enumerable. The corresponding model of computation is Turing machine. Productions are of the form alpha gives me beta. Alpha and beta are variables and terminal, their combination. V in a sigma star. Alpha contains a variable. Alpha contains a variable. Below that, more specific, called context sensitive, and the corresponding model of computation, we have not studied that. It's some restriction on Turing machine, then it is called linear bounded automata. Linear bounded, that is linear bounded non-deterministic Turing machine. That is also called linear bounded automata. There's some restriction on non-deterministic Turing machine, and that restriction is linear bounding. Area is defined in which the TM can function. So anyway, that is not part of the syllabus. Linear bounded automata, only for the concept, that is fine. Type 1, language is context sensitive. Linear bounded automata, that is a subset of a Turing machine. That is the model of computation. Production, alpha gives me beta. Again, alpha, beta, V union sigma star. Length of beta is greater than length of alpha. This is a context sensitive language or context sensitive grammar. Alpha contains, of course, alpha contains a variable. Regular, finite state automaton. We have regular grammar also, or we have a regular expression corresponding to the regular languages. Now, just for clarity, production rules for type 2. Type 2 is my context free. So A gives me alpha, A is a variable, alpha is a string or variables and terminals. For type 3, that is my grammar is regular grammar, finite state machine is the automata. Grammar is regular grammar. We have defined that, we have seen that. Variable, productions are of the form A gives me AB, A gives me A comma B belongs to variable, A is a symbol, A belongs to sigma. So that is the type of production for type 3 grammar. That is regular grammar. Automata, finite state machine or finite state automaton. Next is higher side, context free grammar, PDA. Third is context sensitive grammar, LBA. Last one is recursively enumerable. The corresponding automata is Turing machine. The most general model of computation is Turing machine. Grammar is unrestricted grammar. Name of the language accepted is recursively enumerable language. And still, there are some languages which are not even recursively enumerable. Example, that the last column, production rules, grammar, languages, automata, production rules, example. Many examples we have already seen. Once again, repeating. A raised to n, B raised to n, C raised to n. That is a recursively enumerable language. You just in the example of unrestricted grammar, this one, A raised to n, B raised to n, C raised to n. This was corresponding unrestricted grammar generating A raised to n, B raised to n, C raised to n. So that is my type 3. That is the outermost is type 0. The innermost is type 3. So that is my type 0, A raised to n, B raised to n, C raised to n. That is a recursively enumerable language. This is one example of a recursively enumerable language. Next is type 1, context sensitive language. Grammar is context sensitive grammar. Here also I can have a context sensitive grammar generating this, because this is unrestricted grammar. This is also example of a this grammar is also example of a context sensitive grammar. Length of beta is greater than equal to length of alpha. That is requirement number 1. And left hand side must contain at least a variable. That is also there. Length of beta should be greater than equal to alpha. That constraint is not there in the case of unrestricted grammar. That constraint is not there in unrestricted grammar. You can see here. Here is not there. This one. Unrestricted grammar, no constraint. Alpha contains a variable, but size of beta should be greater than equal to size of alpha. That constraint is not there. It is there in context sensitive grammar. Length of beta greater than equal to alpha is there in context sensitive grammar. Corresponding language is context sensitive language. So this is an example of a recursively enumerable language as well as context sensitive language, type 0 and type 1. Type 2 context-free language. Again, you've seen many examples. We have worked out many examples. One more example, A and B N, A raised to N, B raised to N. That is a CFN, type 2 language. I have to just match A's with B's. I have to compare A's and B's. I don't need to compare A's, B's and C's together, which was the case here. That become a recursively enumerable language. This is a context sensitive, this is a context free language. This one is a context sensitive language also. We have context free grammar for generating this. This is an example of a CFN, A raised to N, B raised to N. Of course, I can have a Turing machine accepting this. I can have linear bounded automata accepting this. That is how this hierarchy is there. Innermost is regular, then context free. Most powerful is this recursively enumerable. Most general is recursively enumerable, type 0. If a language is regular, definitely it is a context free. Definitely it is a context sensitive. Definitely it is recursively enumerable. Vice versa may or may not be true. Similarly, a language is context free, then definitely it is context sensitive. It is also recursively enumerable. Likewise, context sensitive languages are recursively enumerable. Fine. So that was our example of type 2 CFL, and if I want to have a regular language, then A raised to N, N capital equal to 0. Type 3, our regular language, corresponding model of computation is finite automata. Example is A raised to N. When I compare A's and B's together, the model of computation is PDA. When I compare A's and B's and C's together, the model of computation is linear bounded automata or Turing machine. LBA is nothing but a non-deterministic Turing machine with certain restriction. With no restriction, it becomes a normal Turing machine. This is Chomsky hierarchy for classification of languages, grammar, etc. This is our Chomsky hierarchy mainly considered for classification of languages, type 0 to type 3. And we have seen grammar, languages, automata, production rules, examples. Is anyone asking me a question? Anyone? Okay, so with that we complete our syllabus in the course Theory of Computing. Most of the topics we have discussed and completed in the stipulated time. This will be your syllabus for end semester exams as said earlier. You can stop recording, Deepali.